Hello, this is Professor Steve Latender with Green Mountain College for the course 5040, Energy of the Environment. So in this brief tutorial, I just wanted to go over with you some of the basic concepts that you'll be working on for the energy math problem set number 2 here in week number 2. So let's go ahead and get started. So first off, with many types of information and data, it's important to understand how things change over time, in particular with energy usage. So we've got two concepts here to review. The first is an ordinary growth rate, and that is how does a value change from point A to point B, and we reflect that as a percentage, ordinary growth. And the second concept I'll get to in just a moment is what we call compounded annual growth rates, and I'll define that at that point. So an ordinary growth rate, say for example, in 2010 we used, say, 14 quads of energy as a nation, and today we're consuming 18 quads, and quad stands for quadrillion BTUs. We could use this simple equation here to calculate what the percentage growth was from that point A to point B. It's a very simple equation here. The percent growth, you take the current value minus the past value, then you divide that by the past value, and that's going to give you a decimal. And to convert that into a percentage, you would of course multiply that 100 by 100. So again, very, very simple concept here, ordinary growth from point A to point B, and we can use this formula to define what that growth rate between periods was. Okay, a little bit more complicated here is a second concept related to growth, and this is the compounded annual growth rate. So if we look at, say, 2005 to 2015, it's a 10-year period. We can calculate, if we have the past value and the current values, we can calculate this compounded annual growth rate, which tells us on average how did the change in this value occur from year to year. So the compounded annual average growth rate tells us on average per year how much did the value increase. And so this formula is a little bit more complicated. You've got your ending value divided by your beginning value, and then you have to raise that to the power of 1 divided by the number of years. In this case, that would be 10 years. So you may have come across this in other courses, this idea of exponential growth. An exponential growth function is any function that grows at a positive rate on an annual basis. And eventually these exponential growth functions will look like this classic hockey stick J-curve, where all of a sudden the value begins to rise very rapidly. And so again, we can use this calculation to see on average each year how energy use is increasing or perhaps decreasing, and that helps us to understand the system or what we're looking at more deeply. The other benefit of these growth rates that we can calculate, ordinary growth or compounded annual growth rate, we can use these to project into the future. We can say, okay, if we grew by 20% between this 10-year period, what would we expect if we grew at 10% over the next 10-year period? We can project out what the future value would be. And here I have the simple equation for that. Future value equals your present value times 1 plus r, and r would be your growth rate. And similarly, for compounding growth, again, this is a value that's increasing at some positive rate each year. The future value equals the present value times 1 plus r raised to the power of n, which is the number of years. And again, this is really one of the benefits of doing these growth formulas. You can project into the future, assuming that historic growth rates continue into the future. And you'll be doing this for this problem set here in week number 2. I also just want to take a moment. I know in week number 1 we introduced the concepts of conversion efficiency and energy return on energy invested. And these both are very critically important concepts, and we do a little bit of mathematics around these concepts. So both of them have on the top, the numerator of the ratio is energy out, and then on the bottom, the denominator is energy in. And so energy conversion efficiency is you're going from one form of energy to another form of energy. And so we know, based on the laws of thermodynamics, that that is always going to be less than 1, because we can never convert with 100% efficiency from one form of energy to another. Some systems can be very efficient. For example, an electric motor can be 95-97% efficient, converting 95 to 97% of the electrical energy coming into the motor into mechanical shaft motion. So that's conversion efficiency. Now, energy return on energy invested is more of a broader concept, and it's looking at energy extraction processes. So you put some amount of energy in to drill a well, and that process yields energy coming out of the system. And so this ratio, again, is energy out divided by energy in. And it's not really a conversion efficiency concept. It really is telling us what is the efficiency of an extraction process. If we put 1 unit in, if we get 5 units out. So this ratio, we would expect it would always be greater than 1. Because if you're putting energy in and getting less energy out than you're putting in, then that is not a long-term sustainable process for energy harvesting and extraction. Basically, if you're putting more energy in than you're getting out, that it's not economically or physically worth the effort. So I believe in this problem set you'll do some energy return on energy invested calculations, and I just wanted to make sure that there's clarity in terms of that concept. Although it's the same ratio, energy out over energy in, as a conversion efficiency is a very different concept. So that EROEI, energy return on energy invested, again would be a positive number. Say it's 5 to 1, and oftentimes we share this with the top number, colon, and then the denominator. So there's 5 units out for every 1 unit you get in. And then the net energy, the amount of energy after what you've expended to extract the energy, in this case would be 4. You put 5 units, you get 5 units out, and you put 1 unit in. So therefore, your net energy that you get out from this process would be 4 units. And that, again, is a very important concept that we've been studying. There's also another important way that we often look at energy generating technologies is what is the embedded energy in the system, and how much does the energy generating system produce on an annual basis. And we can use those two numbers to come up with what energy economists call the energy payback. So how many years does it take, for example, a wind turbine to produce energy that would be equal to the amount of energy it took to manufacture the turbines and the tower and deliver the system and install the system on site. So that total embedded energy divided by the annual energy output will give you what we call the energy payback in number of years. And there's lots of studies out there that have done this for different technologies. My understanding is that a wind turbine will have an energy payback which is quite rapid, even oftentimes less than 1 year. So within 8 months or 9-10 months, the wind turbine will have generated as much energy as it actually took to produce, manufacture, deliver, and install the system. So it's in a sense it's an important characteristic of various energy generating technologies. Another concept you'll work with this problem set is what we call the load factor, and this is specifically to electricity usage. So electricity, of course, is this very unique source of energy that's produced and consumed at the same time. So the entire system is built around the ability to deliver that peak amount of energy that a building or a system uses. So this load factor gives you a sense of how that peak demand for energy relates to the average demand for energy. So for example, your home may be using 1 kilowatt of energy on average, but in certain hours or certain times of day, you've got your hair dryer on, your hot water that uses electricity is on, if they're all on simultaneously, the instantaneous demand for power will be much greater than that 1 kilowatt. It could be up to 3 or 4 kilowatts. So this ratio of the average power draw of your home divided by the peak power draw tells us what the load factor is. So maybe 30, 40, 50%. So I guess an analogous situation is there's this saying out there says you don't build the church for Easter Sunday Mass. So right at the church is built, it's got a certain amount of capacity, and on those peak holidays it's jammed to capacity, but on average there's many seats that are available. So the same kind of concept is you have to build the infrastructure for electric power production and generation to meet the peak demand. However, we know most of the year that peak demand, that demand for power will not be equal to the peak. It'll be the average demand. And so this load factor of 40-50% is an important statistic that we can look at, kind of the efficiency of the overall system in terms of infrastructure and delivery of energy. So I think with that you should be set to do the problem set here in week number 2. And of course I'm available by email, or give me a call if you have any questions. And I think we'll end there. Thank you.